An international research team has developed a method to manufacture two-dimensional polymers with the thickness of a single molecule. The polymers are formed on a surface by the action of light. The discovery paves the way to new ultrathin and functional materials. The quest for new two-dimensional materials has rapidly intensified after the discovery of graphene, a supermaterial whose excellent properties include high conductivity and strength, making it incredibly versatile. Two main approaches are used to create ultrathin materials. In the first, a continuous layer of molecules or atoms is peeled off from the bulk of the material. Graphene is an example of such a material. The other approach, in contrast, involves the construction of the material molecule by molecule by producing bonds between the molecules in various ways. The problem is that the materials are often small, fragile, and contain many defects. This limits the potential areas of application. An international research team has now developed a new method to manufacture two-dimensional polymers. The discovery makes it possible to develop new ultrathin functional materials with highly defined and regular crystalline structures. The manufacture or polymerization of the material takes place in two steps. The researchers use a molecule known as fan-trip. Fan-trip is a contraction of fluorinated anthracene trypticene. This molecule is a merger of two different hydrocarbons, anthracene and trypticene. The specific properties of fan-trip cause the molecules to spontaneously arrange themselves into a pattern when they are placed onto a graphite surface covered with an alkane. The process is known as self-organization. The next step is the photopolymerization itself, when the pattern is to be fixed with the aid of light. The molecules are illuminated by a violet laser that excites the electrons in the outermost electron cell. This causes strong and durable covalent bonds to form between the molecules. The result is a porous two-dimensional polymer half a nanometer thick, consisting of several 100,000 molecules identically linked. In other words, a material with nearly perfect order right down to the atomic level. Since the photopolymerization is carried out on a surface of solid graphite, it is possible to follow the process on the molecular scale using scanning tunneling microscopy. This shows the newly formed bonds in a persistent network. In order to confirm the structure assignment, the research group has simulated the appearance of the molecular networks under the microscope at different stages of the reaction. The researchers see that the simulations agree well with reality down to the tiniest detail, and they can also understand why their specific system gives such useful results. The next step of the research will be to see whether the method can be used to link other molecules for new two-dimensional and functional materials. By improving the method, the researchers will also be able to control and tailor the type of ultrathin materials they aim to manufacture. Creating covalent bonds between molecules requires a lot of energy. The most common way of supplying energy is to raise the temperature, but this also causes the molecules to start moving. So it won't work with the self-organized molecules, since the pattern would blur. Using light to create covalent bonds preserves the pattern and fixes it precisely as the researchers want it. The polymerization takes place in a vacuum, which ensures that the material is not contaminated. However, the final two-dimensional polymer film is also stable under atmospheric conditions, which is an advantage for future applications. The researcher believes that the material will find many conceivable applications. The most obvious application is to use the material as filter or membrane.